So then to the programme for this afternoon, I'm very pleased to welcome a variety of speakers to entertain you this afternoon. And first of all, we're going to hear from Dr. Philippe Escoubet from the European Space Agency and the recipient of the G Group Achievement Award. And Philippe is going to talk to us about the cluster mission, the first mission probing the Sun-Earth connection in 3 dimensions. Thank you very much.
Thank you very much. Good afternoon. I'm very pleased to be here. Thanks to the Royal Astronomical Society for the award that was given to the cluster teams, the science teams, but also operation teams that are very important. So I would like to thank also the cluster PIs who have kept the instrument running up to almost 20 years now. The science operation team at Rutherford, who have also operated and coordinated the instrument for almost 20 years. The spacecraft operation team that we have at ESOC in Germany. And finally, the archiving team, which is also essential to distribute all data to all scientists and allow all the publication. So cluster is the first mission to measure in 3 dimensions because it's the first mission to have 4 identical spacecraft. And if you put them in a pyramid, then you can measure structure, plasma structure in 3D. I will show a few examples of these measurements. But first, what cluster is. These are pretty big spacecraft, about 3 meters in diameter. So you see the size of the engineer there. It's a bit bigger in diameter, around 3 meters, and 1.2 meters high. It's because we wanted to go in a polar orbit, so we needed a lot of fuel to carry the spacecraft to the polar orbit. So we had the 4 of them, and they are identical. And this picture is quite nice because it shows in the room, in the clean room, very nice clean room, you can see the reflection of the 4 others. And these were the first one that were launched as the first Ariane 5 and were destroyed after 40 seconds in flight. So we built, in fact, 8 spacecraft, and they are there on this picture. Also, we built 88 instruments, which was quite a record for the PI teams. These spacecraft are big, but when we deploy all antennas, they are even bigger. These show in blue the wires that we deploy. They are about 40 meters each, so altogether it's about 100 meter cross-section. And the spacecraft are turning very fast, around 15 RPM. So it's not a small spacecraft, but a big cross-section that you have in space. So when you try to approach 2 spacecraft together, you have to be careful then. And we try to approach them to a few kilometers, and we managed with ESOC flight dynamics, so it was quite an achievement. In terms of publication, cluster did pretty well. So from 2001, the start was pretty slow, but then when we started to have the cluster active archive and to distribute high resolution to everybody, then it picked up and went quite fast. And we have kept this rate up to now. So we have nowadays about 220 papers every 2 years. So altogether it's 2,800 refereed paper. And it's interesting to add also to this SO refereed paper, which is even more. They have more than 5,000. So altogether it's 8,400 paper. And this, because this is the first cornerstone, cluster SO were together. And if you compare, for instance, with the second cornerstone, XLR Newton, which is a very successful mission also, it has a bit less paper, 6,000 paper. Of course, it's a bit not fair because SO started much earlier. You had 4 more years to publish SO results. But still, this means that the first cornerstone was still 37% more referee paper at this time. Okay, I will talk about 6 discoveries out of this many paper. Shock reformation, turbulence, magnetic reconnection, roll-up of Kelvin-Helmoltz waves. Also, how chorus waves can accelerate particles in radiation belt to very high energy. And finally, I will finish with aurora mechanism and sources. Shocks are everywhere. You can find shock in a nebula, the Cat's Eye Nebula or the Orion Nebula, but also in young stars, which have a strong solar wind. You can see LL Ori and the nice, very nice bow shock there. And also in supernova, the well-known 1987 beam. However, you can study shock only very well in situ, because you can measure all parameters, all plasma parameters that you need to understand the shock. We did that for many years, but recently we could approach two spacecraft to very close distance. On this occasion, it was 6.5 kilometers. We had C3, cluster 3, and cluster 4 at this distance, and we were not expecting much difference. However, when we plotted the magnetic field, it's here, cluster 3 is in red and cluster 4 is in white, and the shock ramp is there. You have an increase of magnetic field because you compress the magnetic field towards the Earth. And cluster 3 shows smooth, rather smooth increase in the shock ramp. However, cluster 4 shows this big spike, a very small region here, about 3 kilometer distance. So it's an electron structure that is very important for reformation of the shock. The shock is always moving in space, and these changes then help to reform the shock at another place. And this observation also agrees with the gradient catastrophe model, so it's helping also to validate the model of shocks. Turbulence, I find a nice definition of turbulence in Wikipedia. Turbulence in fluid dynamics is a fluid motion characterized by chaotic change in pressure and flow velocity. So it's quite a simple definition. And you can have turbulence in waves, fast-flowing rivers, storm clouds, or also smoke coming out of a chimney. Turbulence is caused by excessive kinetic energy in fluid flow, which overcomes the damping effects of the fluid viscosity. And finally, in turbulent flow, you have vortices forming, and they appear at many sizes, which interact with each other. And what we see in plasma is that we form first big vortices, and then they go down in size, and this is what we call the turbulent cascade that we get in plasma. So also turbulence, you can find that everywhere. In nebula, this is a very nice picture of the Crab Nebula. All this fine structure is believed to be playing a role. Turbulence is believed to be playing a role. However, we find that also close to the Earth. We find that in the solar wind is in the region that we call the foreshock. This is a special region because we get in this region reflection of solar wind coming back towards the sun. And this interacts with the incoming solar wind. So you get these also waves and turbulence in foreshock. And you get also turbulence in the compressed solar wind, what we call the magnetoschist, in front of the Earth's magnetic field. So I will show an example of data in this magnetoschist region. So this is the magnetic field coming from the 4 spacecraft in different colors. We have cluster 1 in black, cluster 2 in red, cluster 3 in green, and cluster 4 in blue. And this shows the variation of the magnetic field divided by the average of the magnetic field. And you can see that the magnetic field is varying a lot. It's between 15% to up to 80%. So the variations are much stronger than the average magnetic field. And you can also see that there are tiny differences. You don't see only one curve. You see all the color appearing. And this tiny difference then helps us to understand what kind of wave we have in this turbulence regime. You can apply then 4 spacecraft techniques. One of them is called the K-filtering. This is a French method. German had another method, which is called wave telescope, but it was more or less the same techniques. And the way you compare the 4 spacecraft, and then you put the wave power that you receive on the 4 spacecraft, and you put that in a K system. This is a wave number. So you have KY, KX, and KZ system for one frequency. And then in this system, you see appearing this hotspot, which has strong power. And this technique allows us then to differentiate using model the different modes of waves that you have in this turbulence. And in this example, we could find mirror waves, Alphen waves, and also slow mode waves that were identified at the same time. And this is where you need the 4 spacecraft to identify with these waves, because with only one spacecraft, then you can only measure polarization, and then you cannot explain why you have fluctuation, why you have so many waves, because they are all mixed together. Magnetic reconnection is also a quite important topic in cluster, also especially since MMS, also the NASA mission, is also running since a few years. Magnetic reconnection on this diagram is quite simple. You have two magnetic fields opposite to each other. One, for instance, is a solar wind, and one is a magnetosphere, and then they reconnect. And this reconnected field line is quite important because you can have solar wind plasma entering the magnetosphere and reaching the Earth, or you can have Earth plasma leaving the magnetosphere and entering the solar wind. And one interesting aspect of this reconnection is that this can be of a very large distance. This was shown in the solar wind using 3 spacecraft very far apart. It was 8 spacecraft on the 2 first panels, cluster on the middle panels, and then wind. And they see exactly the same current sheet and the same reconnection jet. We show here the magnetic field, the 3 components, and the big change are in the busy component. You see a big change between positive and negative busy. And at the same time, we see this big flow of plasma, and this is the sign that you hit or you cross a reconnection line. So this is seen at ACE at about 1:30. Then about 1 hour later, we see exactly the same thing at cluster with a change of BZ and the high-speed jet. And you see that 2 hours later at wind with the same BZ and the same jet. So Fan et al. Believe that it was the same reconnection line extended over many area of distance, many kilometers of distance. And when you compute the distance, you find that it's up to 2.5 million kilometers. So it's about 10 times the distance from the Earth to the Moon. And this would be a single current sheet with the same reconnection. So people were surprised to have so long reconnection line. In fact, after that, we found it could be even longer. With stereo, it was used, and they found, I think, 1,200 or something like that. And all spacecraft were on this side of the reconnection, so they see all this flow going down, not seeing the upper one. And in fact, it was so nice story that Nature decided to make the cover for this one. And in our field, it's very rare to make the cover of Nature. Reconnection also can happen at much smaller scale in the Earth's magnetosphere. This is one of the first observations. And the thing you can do also is to compute curvature, the curvature of the magnetic field. It's a simple calculation. It's, you take the magnetic field and you multiply by the gradient of the magnetic field. The gradient, you get it from the 4 spacecraft measurements. And with that multiplication, you get the curvature. And curvature is very important because when you get this reconnection line, you get on this side a field line which is like that, and on the other side, the field line is like that. So the curvature is opposite. So if you cross such X line, you should see opposite curvature. And on this middle plot, this is what we see. The curvature is plotted, and you see it negative first and positive afterwards. So we see really this crossing of this edge of this kink of the magnetic field. And of course, the flow of plasma leaving the reconnection is also observed in the last panel with the flow going negative and positive. So in fact, when you see this reconnection line, it's not the spacecraft crossing the reconnection line, but the reconnection line moving through the spacecraft, because the spacecraft is not moving very fast. We could see also reconnection close to the cusp for the magnetopause region, and now we are more over the polar cusp region, so above the Earth is there. So cluster was crossing this field line there, and could see reconnection because interplanetary magnetic field was northward. This is interplanetary magnetic field, and then in the magnetosphere is going south, so they are opposite and they can reconnect. So cluster was crossing this reconnection line there and seeing the 2 flows again, one flow in red and the second one there. And this is shown here. We plot here the flow Vx component, and we have one negative, the 1, and one positive, the 2. And the nice thing is that at the same time, we had the NASA imaging spacecraft who could image what was happening over the pole here. And he could take an image of the proton precipitation, and this is shown here. And at the same time, they were seeing this bright spot on the day side near the cusp, and this was linked with the reconnection taking place much further away, seen by cluster. And they have made a nice movie of it showing this particle entering the magnetosphere and then precipitating and reaching the ionosphere. And when they do that, then they can make this bright spot. And of course, these ions enter much further away and are observed with cluster. The last point on reconnection, what you expect theoretically is that at the center of reconnection, you should not have magnetic field anymore. It should be a null of magnetic field because you are really at a peculiar point. Of course, this position is very small. This null is very small, so it's very difficult to catch it. We rarely catch such null. But what you can do is for spacecraft, if you have the four spacecraft around this null, and then by interpolation and comparing the measurement, you can tell if there is a null inside the four spacecraft or not. And we use for that a Poincaré index, a Poincaré method, that can tell you if it's 1, then this means that between the spacecraft you have a magnetic null, but if it's 0 here, you have no null. So it's a very good method also to find where you have reconnection. And this is only at the heart of reconnection. Now, Kelvin-Helmoltz waves, these are nice waves that you can see everywhere and also in the sky. This is when you have two flows of wind or plasma going against each other, and then they form these very nice waves. Of course, you can see it because you have cloud here, but in plasma, you cannot visualize it. So we try to visualize it with simulation and with observation. And the nice thing that was found with cluster that is also seen there is that sometimes it's not only a wave, but it's rolling up. So you have the thing forming also a vortex, which is also seen in the cloud there. And after a while, then this disappears and they collapse. So this is what we see also in cluster data and in simulation. This is a simulation showing MSG simulation showing the magnetospheric side here and the magnetosheath side there, and the formation of this wave. If it would be a normal wave, you would not have this special tongue there that you see when they start to roll up. And the way to see that they are rolling up, if you have a spacecraft on this green point, this is the density plotted here. So green is fairly high density. So a spacecraft located here would see higher density than a spacecraft located in this blue region. And also, this spacecraft is further in the magnetosphere than the other one, which are further out. And this is what we see on cluster at these red bars here. We see cluster 1, which is closer to the Earth, seeing higher density than clusters 3 and 4, which are further out. And this is the only way to see that these vortices exist, and it's not only a wave. And this is the first time that it was observed with cluster, because you needed a multi-point measurement to observe that. And this is a sketch that was done. So you have this flow of plasma from the solar wind along the flank of the magnetosphere, and then these vortices form. Then they move down because of the flow in the magnetosheath and solar wind, and then they collapse there. An important aspect, during their collapse, they can also make the solar wind entering the magnetosphere. And also, since magnetic field is quite turned inside these vortices, we have seen also sign of reconnection inside these vortices. Now about radiation belt. These are very important aspects because during big storm, you can have effect on satellite, but also on the ground. So people are very interested in what's happening in radiation belts. And this is a measure in 2004 of the radiation belt flux of MeV electrons. These are very energetic electrons, millions of electron volts. And this plot shows their flux as a function of L. L is more or less the distance from the Earth in Earth radius. So typically it's around 4. So this is this ring around the Earth, around 4, or where you have the higher flux of electrons. And this is varying depending on activity in the magnetosphere. It's varying, and in the solar wind. However, during one of the biggest storms I think that we had in the last 20 years, this was in 2004. It took a few weeks, October, November. We saw a big change in radiation belt. The radiation belt disappeared at 4 and then reappeared at much closer distance from the Earth, around 2. This is a zoom here down there of this small period. And you see that they disappear around 4 and then they reappear around 2. And it was not clear how they could reappear as fast. In a few hours, they could reappear and be energized. And Horn et al. Showed that chorus waves that were observed on cluster at the same time were very intense. You can see them, this chorus wave, in both electric and magnetic component, and this is close to the Earth. And this wave, they can interact with particles and then increase their energy up to millions of electron volts. And they could show at the same time, using their model, that this would accelerate this particle. And much better than a typical model of radiation belt acceleration like radial diffusion. Now about aurora, cluster was not done to study aurora because we are much further out. So we cannot see aurora, but we can see some aurora. And in fact, when you have these auroral arcs, quite bright, in the middle, you have this black stripe also, very often. And this is what is called a black aurora. In fact, it's a reverse of an aurora. Instead of accelerating electron down to the ionosphere and producing light, you accelerate electron up. So the potential structure is just opposite. So the system is the same. And this acceleration up, then we could see it with cluster. We were above it, but we could see it then with cluster. And the nice thing you can do, when you see a picture like that, the aurora is not moving. But if you had the chance to see aurora, you could see that it's moving very fast all over the sky. And this is moving. And the nice thing with cluster is that we cross these field lines and auroral structure in a string of pearls with one spacecraft following each other. So we can really monitor how they move in space and understand better why they move also. And this is an observation that was done quite early in the cluster mission, showing the potential structure. So you have a potential drop aligned with the magnetic field that is accelerating electrons up. And we were crossing this structure, and we could see electrons being accelerated to 0.7 keV. This was with the first spacecraft. The seventh spacecraft saw a stronger potential structure with stronger electric field. And now the electrons were accelerated stronger to higher energy to 1.2 keV. And this was only less than 2 minutes after. The third one saw even stronger energy, 2 kilo electron volt, and then about 2 minutes. And then the last one did not see anything. No acceleration of electron, nothing. So it seems to have disappeared. So Marklund et al. Then looked at the modeling of this structure and could model it quite well, modeling the ionosphere, the content is the ionosphere. And they could show that this potential structure, when they form, then they pull electrons from the ionosphere. So they create this density cavity at ionospheric altitude, and this grows as the potential grows, and you accelerate electron to higher energy. And then when they have depleted or this density is too big, it cannot anymore collect or attract electrons. And this is when the potential drop stops and this black aurora stops then. So it was a way to see with even the fourth spacecraft was very important to see why it was disappearing then. Now, these are bright auroras. This is quite an old picture from the first spacecraft who was doing global imaging of auroral oval. This was Dynamic Explorer 1. This is published by Frank et al. In 1982. And an interesting thing that was not understood for many years, almost up to now, was this transpolar arc. This is quite a typical, you see the oval auroral here, and this transpolar arc is forming this theta letter, so this is why they call it theta aurora. And a very good conjunction between cluster image could then solve this mystery of showing from where they were coming from, this particle forming this transpolar arc. So we showed here the image movie, and then the spacecraft position with the red point. And you will see forming this transpolar arc. And when it's crossed with cluster, we see this more energetic particle. So for the first time, we can look at the 3D energy distribution of this particle and tell from where they are coming from. And if we take, for instance, this time here, where we are exactly in the middle with cluster of this arc, we could show that the electron distribution, so this is along the magnetic field, and this is perpendicular to the magnetic field. And we could see that the peak was around 90 degrees. This was showing that it's in fact closed field lines, and these particles are coming from the center of the magnetotail. And then there is a deformation of the tail, and then they can enter in the polar cap. Of course, this is only one example, but on this example, we know for sure that they are coming from the plasma sheet and not from the polar cap or from external region from the magnetosphere. Finally, a small advertisement. When we rebuild cluster 2, in fact, we call the first spacecraft Phoenix because we did not have yet budget to build the other 3. So we started to build one. And this was 20 years ago. And this year, we will celebrate 20 years of cluster in September 2020. So everybody is welcome. Before I finished, I would like to thank all the team that are behind all these results. First, the Science Operation Working Group, who is made of PIs and all the science operation teams. The Science Operation team at RAL, who is doing the coordination of all the instruments. The Spacecraft Operation team at ESOC. And finally, all scientists that are publishing all this data. Thank you very much.
Thank you so much, Philippe, for a fascinating talk. So many results. What a wonderful mission. OK, we have time for a few questions. And please wait for the microphone. Yeah, over that way. Thank you. You can just stay here. There are questions. What shall I do that for you?
Philippe, what's the future for cluster?
Yes, we are preparing now a new extension. 2 years ago, we proposed a scientific case for 2 years extension covering 21, 22. And this we will look for confirmation. So if nothing happens on the spacecraft or instrument, we may get this confirmation, so up to the end of 22. But we would like to propose also to go up to the end of 25. And the key aspect there is to make collaboration with the new mission that will be launched soon, SMILE mission, because this will be very complementary with SMILE and with also other missions like NASA mission. So we are preparing that, and the result will be known then in June of this year. Then.
Fantastic. Yes. Question over here.
Thank you very much, Philippe. You made at the beginning, and actually through your talk, the strong point that these processes that you're studying are of universal applicability through astrophysics. So how do you see the cluster results percolating out into the rest of astronomy and astrophysics?
We can see that when we see where these papers are published. The key result on turbulence are published not in our journal where we publish JGR, GRL. They are published in more physical journals. And they are a lot of citations. They have a lot of citations. So I think all these papers on key physical process, they are seen by many other people because they are published in these specific journals. So I think this helps to have a broader range of distribution.
Any further questions? OK, if not, thanks very much, Philippe.